Good morning, everyone. Welcome to the Angle DC's first webinar. We're just going to leave the screen up here for the next couple of minutes as people log on, so they have a clear instruction to get audio via the teleconference system. Okay, so just bear with us a couple of minutes and then we'll start the webinar. Okay, good morning, and thank you all for joining online. This is Angle DC's first webinar, and it will be focusing on supplier engagement and the MVDC technical design. If you have any questions that aren't covered in this session, feel free to give me an email, and I'll be sharing the webinar video, hopefully on the website or at request. Okay, so we'll just go through the webinar and it'll begin now. Okay, so I'll go through the agenda for today. From 10 o'clock till 10:25, we'll have a project overview with Kevin Smith, who's the principal project manager for Angle DC. He'll also talk about the supplier engagement process and the main people who are engaged. And from 10:40 till 11 o'clock, we'll pass over to Dr. Norman McLeod, who's our HVDC expert from Parsons Brinckerhoff. And then following that, we'll go to Dr. Jun Liang at Cardiff University, who is one of our project partners, and he'll discuss their body of work. And then we'll go back to Kevin, and we'll discuss all of our stakeholder engagement activities for the project. And then we'll have a 10-minute Q&A where I'll chair this, and you can fire questions at me, and I'll direct that to our panel of experts. And then we should be closing the presentation at 11:30. Okay, so I'm just going to pass over to Kevin Smith now to go through the project overview.
Good morning, everyone. This is Kevin Smith. I'll just go through a few slides. I'll start off with an introduction of Angle DC and explain a bit about the project and why we've initiated it. It's really stemming from the fact that there's a lot of high level of penetration of generation in Anglesey, particularly in that North Wales area. And you can see on the diagram that we have alongside there that the squiggly line between Llangefo and Carnarvon and Llanfair PG and Bangor is the Menai Straits, is illustrated there. And we currently have two connections across to Anglesey from the mainland at 33 kV. And then the only other connection is the 400 kV, which is the pale blue that you can see between Bangor and Wilver. What this means is that obviously we'd like the power flows to go through the 400, but because we run a meshed network in SP ManWeb, we do have this parallel path for the 33. So what we end up having is quite an amount of power is flowing across the 33 network. We've got the added complication that when Wilver, the new Horizon nuclear station, comes on stream, the output of that being about 2.8 gigawatts will actually cause about 50% of the circuit capacity on the 33 to be used up just on the kind of leakage parallel path of the power transmission from Wilver across into mainland England, Wales and England. So one of our solutions to deal with this is to look at how we manage those power flows, and the MVDC route has been one that we've been keen to explore and obviously turn into a trial project. So what you can see there is we've given you a bit more detail, but you can see that the 33 connections across to the island from the mainland are going to be supplemented by one of the existing circuits, which is a double circuit between Llanfire PG and Bangor, and that's the one we're going to turn into the DC link. It's a little bit unique in as much as it is a double circuit, and it goes cable to cable to both ends, and it's literally just bunched on the breaker, and that gives us the opportunity to turn each discrete cable circuit into a pole of the DC link. Once we've done this, we will then open the other feeders across to the island, and the DC link will be the only connecting point, and that obviously gives us the opportunity to manage power flows. The next slide just gives you an illustration of the system diagram for the 33 network on the Anglesey Island and just off it on the Menai Straits. And you can see the circuits there in a bit more detail that I'm actually talking about. So between Carnarvon Grid and Llangafo, we've got the 33 circuit, which will be running open split following the operation of the DC link. The link that you can see that's got the double circuit in it, where you can see the 30 MVA DC, is where the two converter stations are going to go, which will sit either side of those cable circuits. And there's a red line to the right-hand side of that between Llanfire PG and Bangor Grid, and that will be a new 33 circuit that we're going to install. Obviously, operating the existing circuit at DC, and we'll be operating them at plus or minus 27 DC. We're a bit unsure and a bit nervous of how this will pan out in terms of the effects on the cable, and I'll come on to that a bit later. So one of the issues that we're trying to de-risk the project is by having this additional circuit, which we also need to get the DC link circuit off while the work's being undertaken and the converter stations are being connected. So that's an additional circuit that we're putting in, and that'll run very close to the existing circuit. So we talk about the project principles. The left-hand side diagram shows you the existing cable circuit. It's interesting in as much as it's got a small section of overhead line. It's only 5 spans, and it runs for about 500 metres at the far end near the Llanfire PG substation. So that will give us an opportunity to see how DC operates on overhead line circuits, the effect on insulators, and whether there are any detrimental effects or things that we need to worry about there. Obviously, that brings into play a number of other points to consider, such as transient faults, which will occur from time to time. This area is quite exposed, and lightning strikes and storms are quite the norm. You can see on the diagram on the right hand side the two poles, so you can see the two circuits between the substations. There'll be a transformer, the MVDC converter, thyristor bank. It then splits into the two poles. We're going to actually put some isolated earth switches and disconnectors on the outgoing circuits to give us ease of earthing up and isolation for changing pin insulators or faults on the actual circuits themselves. And then it goes in a mirror image back at the other end substation. You'll also see a couple of other things on there. Near the overhead line, you'll see some loops. Towards the right-hand side of the cable section, you'll see some loops which go into a cabinet. And this is the HMS, which is short for Holistic Monitoring System. And what this is really all about is for us to look at the signature footprint of the cable in terms of parcel discharge, and try and understand the level of sort of the health position of the cable, and for us to continue monitoring it following its DC conversion, and that will give us an opportunity to see whether there's any further deterioration of the cable insulation through the operation under DC. You can see further down there that there's the voltages that we're going to operate it at, so it will be plus or minus 27 kV DC, and there's a few boxes at the bottom of that slide which just illustrate the benefits. It will give us control of active power. We'll be able to optimize voltage, reduce losses by controlling the power flows, and obviously use the assets because of the increase in capacity it gives us operating at DC rather than AC, and hopefully that will avoid or defer further reinforcement. The next slide is a quick slide I'll just run through, and that's the Bangor grid site. You can see it's a fairly typical grid site with the 132 on the right hand side and the 33 outdoor compound on the left. So you can see the red boxes are showing where the big box in the middle top of the screen is showing where the MVD converter station is going to go, and the left hand small red box is the spare bay, which we're going to introduce the new cable circuit connection. To go into a bit more detail about what a converter station actually looks like inside, what will be inside that big red box on the previous slide, and that is, it's made up primarily of the transformer, which is the bottom left, item 2. Transformer coolers is the item 12. We've also got the IGBT, which are the thyristor bank coolers, which is item 11. And we've also got some DC reactors, which is item 3. The main event is in the IGBT module room, which you can see, which runs down the slightly right of centre. Obviously that's all water cooled, and the cooling goes through the fans and the radiators. It's an air conditioned room, it's a dust kind of free type environment, etc. And then to the right hand side you can see this is where the kind of ancillaries are, and that's the cooler pumps, the control room, which will have the kind of the desk with the workstation in, which gives us opportunity to monitor and operate the DC link. And we've also got coolers and a DC switch room, which is in there as well. You can see at the bottom we're also tagging on a small additional room, which will be a visitor centre, and it will give people the opportunity who wish to see the converter station in the flesh, be able to come to site, and we'll be able to talk them through it and take them around the site. We won't be able to take anyone into the IGBT room because that will be an excluded area, as will the reactors, but other areas we'll be able to show them around. The next slide, again, I'll quickly skip on because that's just a layout of the Landfair PG end, and you can see to the top of the land that we own, is the two circuits, the overhead lines coming in, which currently are the existing Landfire PG to the Bangor, which will be converted to each of the poles, the respective poles of the DC link. The next slide is showing the new cable route, and you can see it kind of follows a green line which kind of hovers underneath, and that's the existing 33 cable circuits. So we're pretty much going to follow them, and we need to go across the Britannia Bridge on the other side, up a few roads, across an A55 bridge, which is a bit of a motorway type bridge, and then through some land and into the substation. The action of actually crossing the bridge with the AC cable didn't give us much trouble, and we're in sort of consent discussions with Network Rail, who happen to own the bridge, because the bridge is a double decker which has a rail track on the lower deck and road highway on the upper deck. Obviously, in our discussions with Network Rail, what's immediately become apparent was the fact that with the existing cables and the proximity of them to the existing railway infrastructure and assets, i.e. signalling cables and track rails and track positioning systems, and operating them at DC and the consequential magnetic field, with operating two poles which are separated by a number of meters, then give rise to obviously how we're managing the risk of any cross interference, and I'll come on to that in a further slide later on. I'll quickly run through the programme structure. We split this project into 6 work packages. The first work package was fundamentally the design of the DC link to come up with the functional specification and the procurement documents and spec. And we also did exactly the same for the holistic monitoring system. And we were mindful of the fact that although there's a number of companies offering partial discharge for AC, there's not so many who've got any experience on the DC side. The work package 2 is fundamentally the installation and procurement site preparation of the DC link vis-a-vis the converter stations. Work package 3 is the new AT cable and bringing that into play. Work package 4 is the holistic condition monitoring system, which is the one, as I mentioned, which is going to monitor the cable health both before and post switching over to DC operation. Work package 5 is data analysis. As you can imagine, there's an awful lot of monitoring and an awful lot of data being gathered by this project, so analysing the data is a big part of it, and taking the learning from that. And we've engaged Cardiff University. They've got a strong team there in this area, and they're going to do a lot of the data analysis for us. And we've got Dr. John on later on, who will take you through some of the activities that they're doing. And work package 6 is obviously dissemination, as per all NIC projects. Dissemination is a big part of it, and just being on the call today is all part and parcel of that dissemination activity. The project structure is fairly simple. It's not a big project group. We undertook to establish the steering group to give some executive control and steer and possibly backing, if you like, with a number of parties. We've got SP Energy Networks, we've got some directors and some of the other key managers and players in the chain of staff who will be delivering it. We've also engaged with Welsh Government, who were very supportive of the project, and we've got a number of them on the steering group. We've got Cardiff University, and who are also very key to the steering group is the input and support of the two councils either side of the link, which is Gwynedd County Council on the mainland, North Wales, and Anglesey County Council on the island. I'm the project manager. James Yu did the work package 1 work, which was the design for and specification for the MVDC and monitoring equipment, which is obviously flowed into picking a project partner. And we've got the project partner for the supply of the MVDC equipment on a supply and install contract is GE Power Conversion. Our other partner in the project is the academic partner, which is Cardiff, which comes under work package 6. And we've got the HMS supplier, supplier, and that was HV Parcel Discharge, based in Manchester. We are undertaking the actual build works and the concrete, the housing, the installing of the new cable, and preparation of the site for all the new systems, and that's been undertaken by Iberdrola Engineering Construction, who are a subsidiary of Iberdrola, of which Scottish Power is a subsidiary, so it's a bit of a sister company. And myself and Andrew Moon are the key sort of drivers of the activity in terms of dissemination, project support, knowledge transfer, reporting, documentation, and as you can imagine, there's an awful lot of control activities. And we link into legal, commercial, health and safety. There's new health and safety procedures having to be written for this type of device, which will be shared at a later date. How we integrate into our policy and design and operating, and there's an awful lot of SCADA and telecontrol activity going on as well. The project plan on the next slide is just gives an overview, a block diagram of where we started back in January of last year, 2016. And the first thing we did really was to pull together the DC link and the holistic monitoring specification and go out to tender with them. We issued them. We've moved them on in as much as the work package 4, a bit further down. The holistic monitoring system has been installed back in the last year. We're still in the final commissioning phase, and it'll be up and running probably in the next 2 months, so we'll be well ahead of the game on that one. The MVDC link, we went to tender on that, and we finally let the contract in the last month to GE Power Conversion, and they are now full steam ahead in terms of manufacture and bringing that ready into play at the back end of next year. The AC system, which is the new cable, we've been seeking consents in the middle of last year once we decided where we wanted to lay it, and that's ongoing. We have got 1 or 2 issues, as you can imagine, but that's only to be expected on gaining consents for new assets. The data analysis work hasn't started yet, and the dissemination is a constant ongoing throughout the project. We've done a number of things. We've published the HMS technical specification that was published last year, and we're about to, we've already just published the MV DC technical specification that was published in the beginning of February. Our next activity is the commissioning of the HMS for RS. I'll give you an overview of the project, and I'll move on to the kind of supplier engagement. Obviously, there was a lot of things to procure under this project, and I'll talk about some of the things that we've been engaged in and how we went about it. The holistic monitoring system, which is specified under work package 1 and installed under work package 4. We produced the functional specification, I mentioned that. We completed the SDRC, which is available online if anyone wants to see it. We engaged with 6 suppliers for tendering. I have to say, although we had 6 to start with, it wasn't 6 for very long, and it soon became apparent that the being able to monitor and having the software and the systems to be able to monitor once it was transferred over to DC operation, we were down to really only a couple of people who could, we felt had the technical ability and know how to do that. So we operated that tender process early last year, and we awarded the contract last year, and that was awarded to HVPD. We did the hardware. They did the hardware production at the end of last year through to this year, and it was literally in January when the final server went in, and then the connecting up. We had to have some outages in December and January, which wasn't very easy during this time of year, as you'd all expect. But eventually we commissioned the system on site, and it was not fully commissioned yet. Is the bringing the data back through to our office to save us going out and collect it. But we did do a data collection last month, and that was the first set of data, which we're still working on at the moment in of analysis and seeing what that looks like. The next level of engagement with suppliers was the MVDC link. We knew we had to get this ball rolling quite quickly, so we opened the tender literally last April, closed it in May, then went into various rounds of discussion with the suppliers. We had 4 suppliers who were keen and we felt that could deliver what we wanted. We engaged with the suppliers to the level of bringing them to site so they could see where the equipment would go and the size of footprint and the land available, the access. We had one-to-ones with them where we sat down and made sure that they fully understood the bid and made sure that they knew our requirements. We then let them come back with their first stage tender, and following that we sat down with them again, had one-to-ones with all 4 suppliers, and let them go through and fully explain their bid and what they'd included for, what they hadn't included for, and what assumptions were made. And we found that very useful, and if I'm honest, it helped shape and tweak one or two things as to what we maybe hadn't thought about in the functional specification. So that's why we tweaked the specification before we published that. Some of the key elements coming back from the suppliers was the fact that some of the suppliers were within our project budget, some weren't. Some could supply equipment within the building footprint and height. There's a bit of a height restriction on the second site at Llanfire PGE because it's kind of in open countryside. It's surrounded by bungalows. There's an existing substation building, and nobody wants anything that's dramatically too tall built there. So building footprint and height was a big issue. The losses of the apparatus in terms of its performance and efficiency was something that we made a major consideration on. Reliability and maintenance, and obviously we were interested in how they'd used this equipment before, in what context, and whether there was reliability, and they'd had a lot of user hours or years, if you like, of the equipment. We wanted reliability for the equipment when we put it in. We certainly didn't want something that was going to be more off than it was on. So we completed the SDR2, and we awarded the contract, like I say, last month to GE Power Conversion. So the plan for going forward now is the converter station production and installation, and that is planned to be done by Q4 2018. And then there's a small stage of commissioning, which is about 4 to 5 months, which will happen back end of next year into the following year, and then that gives us from Q2 2019 through to Q2 2020, which is the end of the project, to evaluate the operation of the MVDC link for 12 months. I'll talk about the control of the link, because this is obviously a a major factor. You go out and you spend all this money buying an MVDC link, and then the question is what do you want it to do and when do you want it to do it? And that's really given us a lot of head scratching, but we've come up with a system that we feel is right for the link, and that is there'll be 3 levels of control, what we call a basic control, a local control, or backup as you could call it, and a central control, or we some even times call that complex control. We've had a look at we've done a lot of network studies about how the link would operate, what the power flows are, various network conditions and parameters are that would cause us to want to wind the wick up and get it transferring more power in one direction or another, or perhaps we want to manage reactive power to control voltage, either one way up or down, or perhaps we actually we want to block the transfer of power and obviously force it to go through the national grid connection. So we've been engaging with our control engineers, because they're going to be the primary user of the equipment in terms of how it's going to operate. Obviously they're keen that it doesn't require an awful lot of manual intervention. It requires it to operate almost in an autopilot method, so that they have got enough information to understand what's going on, but don't need to be intervening on a regular basis. So we are putting together a specification for a controller that we're going to go out for to later in this year, and our plan is to have it finished by about June, and we go out early second half of 2017 to see who can offer us what in terms of the control system. The basic control is really all about if we lose all the comms to the link, and also worst case scenario for us is we lose the Bangor transformer, the grid transformer at Bangor. What we then really need to do is shut the link down from a power transfer point of view, but we may gain some benefit through a voltage support mode. So that will be something that doesn't rely on telecoms and communication system, and that can be a hardwired setup back at the local substation. So that gives us some assurance then that if something does go drastically wrong, we can switch straight into that. The next level of control is what we call local control. This is an independent system from the central control system I'll talk about in a second. And what this is doing is taking the key parameters that will affect the link operation. And that primarily is the net import or export, which is going on at the 4 grid sites surrounding where the link operates. These are the key areas. Although we run fully meshed across North Wales, as you go further away from the link position, then the effects of other network activity become less and less. So these are the key ones: the Caergiliog grid and the Amlwch grid, which are on Anglesey Island, and the Bangor grid and Carnarvon grid, which are immediately off the island on the mainland. So what this really will come into play when we've got no central control availability, it's got independent comms, it's got independent transducers, it feeds into a local controller, which will be, I'll call it a black box with a control algorithm in, which has got a limited number of inputs, but provides sufficient course control that we don't lose the asset should we lose the central control system or communication lines. Moving on to the central control, this is something that we're looking to integrate into our network management system. We currently use the Power on Fusion package, and we're also looking at a bolt-on to that, and whether we use it within the existing software suite or as an additional function, or whether we use it as a separate one is something to be decided, and depends on what we get offered when we go to tender. But fundamentally what this does, it looks at all the 4 grid transformers that I mentioned, plus 23 primary transformers in terms of input and output to the 33 network, and also looks at all the major 33 generator in feeds. It takes all them values are already in the network management system, so it can take all those values, computate what the best voltage, megawatts, reactive power transfer for the link is, and then fire that out to the local RTU, which we're going to have upgraded to a modern 61850 version, and that will in turn talk to the controller and control the link. And this gives us precise control over the link and helps us understand exactly through power system analysis mapping where the load or generation sensors are around the island, and we can optimize for power transfer and vis-a-vis optimize for losses. I'm going to touch on the Britannia Bridge issue. This has been something which has given us a lot of thought, and what we've had to do is, in talking to Network Rail and understand their assets, we've had to go out and survey the site and understand where the cables are precisely in relation to the Network Rail assets and any potential interference on that. And you can see there's a little 3D diagram and a cross section with the actual measurements on, and they're the outputs of the survey. So you can see that we're approximately about 5.5 meters apart for the cables, and also about 5.5 meters to the signalling cables, but a lot closer to the track position. We haven't got all the dimensions on that diagram, but you can get the gist of it. It's a double deck arrangement, but there's only one train track on one side of the deck, the other one's empty currently. That's a photograph really, which is kind of showing the and hopefully the cable can get the cursor to work on this. And you can see on there you've got the occupied deck with the rail track, and you've got the unoccupied deck. You've got this gap in the middle, which runs along the full length of the bridge. And along here you can see the existing HSL cable. There's two cables there. One's about 40 years old, which is a HSL, standard paper lead single combined, and on the other side we have a cable trough which is put in here, if you can see the cursor moving, and that's the XLPE, which is a newer circuit which went in about 10 or 15 years ago. And we're going to put the new AC circuit in with there, and obviously the other two will be running at DC. So you can see there's quite a proximity there between the railway track and the existing HV cable, 33 cable hanging on the tray work to the side of the deck. So this has caused us really to get into something which was called the Network Rail operate this thing called a common safety method risk assessment and evaluation. And what that means is that we basically need to risk assess and consider all the potential risks that operating the existing circuit at DC may present to the railway, and have that verified, go through an assessment with the Network Rail expert panel of engineers, and hopefully come out at the end of it with agreement that we've managed the risks and we're not going to cause any problem. So I won't go through the wording of this slide, because I've got a small slide shortly which kind of shows you the flow path for this, so hopefully it'll make a bit more sense then. So what we've got to do is we've got to undertake the common safety method risk assessment. That involves HazID workshops, and the output of this is to come up with a safety justification report, which also needs to include a commissioning plan of how we intend to bring the equipment online. And factoring into that very heavily is EMI modelling and assessment of the potential effects of the magnetic field and any potential cross-induction through the ripple effect of the harmonics that obviously will exist in the DC. So we've appointed a company to undertake the CSMRA. It has to be an approved company who's on the approved list for, you know, expert activity in this area, and we've appointed Fraser Nash on that, so we went to tender, and that's who we appointed. You also, secondly, have to appoint an assessment body to assess the safety justification report and make their own independent view of what they think the risks are and etc., and whether they feel all the considerations have been made, whether they've been correctly, whether they are valid, and the outcomes and the conclusions of those assessments and the assessment of risk is fair and reasonable. And we've had to appoint a separate assessment company body, and we've appointed Ricardo Rail to undertake that. We also needed to appoint the EMI modelling company. Now, this could have been done as part of the CSMRA, but we went out to tender, and the company that we felt would offer the best package of work was Mott MacDonald. So you can see there's 3 separate tenders that we've had to go through on this just to get this ball rolling. Then, when all that's done, we go to the Network Rail Engineer System Review Panel. If they're happy with all what we've assessed and all the conclusions and the outputs and the mitigation methods, whatever we come with, we have to do. We haven't had the Hazard ID workshop yet. Then that will give us the the thumbs up to go ahead and install the MVDC equipment. If we do need to do anything, particularly filtration of harmonics or something like that, then obviously doing this pre-installing the equipment gives us an opportunity to factor in some additional filtration on the DC side should we need to do that. We then move into putting the equipment in, energization, set it up. We'll be under restrictions in terms of power flow. We won't be able to do any power flow till it's all been proven that everything's okay, and the actual interference and potential cross induction into the Network Rail assets is okay. So we will have to do some power flows when no trains are running, which will be in the night. If that looks okay, that's fine. If not, there is an opportunity to tweak some of the software firing angles on the thyristor and shift the firing frequencies, which might give us an area of frequency which is less prone to interference than the ones that we would normally run with. So that's one cheaper option to hopefully not give any problems of interference. Then there's the other thing, the consideration that we may need a test train, so that is to actually run a train with no people on it and with power flows and see if all the instrumentation and everything on the test train all operates exactly as it should, and the location of the train in terms of track positioning system is all okay. So if all that's okay, then what we feel we've done is prove that in this application it was safe and okay to apply the DC to the cables near the railway. Now, we appreciate that there's an awful lot of learning to do on this, and we'll be able to transfer that and share that, and hopefully anyone else who wants to do a DC circuit and encounters a Network Rail asset will be able to fall back on this and use this as a reference piece of material to understand how to go about it. Okay, well, hopefully I'll give you a good insight to the project, what it's about, what we're doing, etc. And I'll now hand over to Dr. Norman McLeod, who's from Parson Bringarhoff, and he's been giving us a lot of expert technical support on specifically the functional specifications, etc. So I'll hand you over to Norman now. Thank you.
Okay, thank you, Kevin. Good morning. As Kevin said, I'm providing technical assistance on this project on the DC technologies. What I'd like to do in this short presentation is just to explain in a little bit more depth the technology we're going to use for the MVDC system. So if we go to the next slide, this is just the highlight, if you like. Kevin has explained some of this. We will take two existing 33 kV AC circuits with a nominal power rating of 24 megawatts and convert them to operate as DC. Kevin's explained the cable and overhead lines. I want to talk about that. But what we're going to do is build a MVDC link, which will operate as a single symmetrical monopole. I'll explain this in a few seconds. And this will be based on voltage source converter technology. So this is the most appropriate technology for this type of medium voltage DC application. And again, I'll discuss that in a few moments. This scheme will now operate at 30 megawatts, a 25% uplift of power compared to the existing AC system. We've been quite prudent in our design of the system. We're trying not to push the technology too hard because of the existing AC circuits and perhaps the age of the cables. So we've chosen a DC voltage of plus or minus 27 kV, a fairly esoteric number, but if you do the sums, 27 kV represents the peak of a 33 kV face to ground voltage. So 33 over root 3 times root 2 equals 27 kV. So the concept is we are not stressing the existing AC cables any harder than they're already stressed under the AC voltage. In theory, we could push the voltage higher with DC and get more power. But as I say, we've adopted a prudent approach for this first medium voltage DC link in the UK. So that is the reason for the 27 kV choice of DC voltage. If we go to the next slide. This simple topology shows a voltage source converter link between two AC networks, termed network 1 and network 2. In most DC applications, the two networks are asynchronous, but of course, as Kevin has explained, this is actually an embedded link within a synchronous system, so that both systems operate at the same frequency. But no problem there. The key concept of a voltage source converter is that we have a charged capacitor at both ends of the link. It's used as an energy storage device. And by that, I don't mean it's like a battery. It is merely a transitory storage of energy from AC to DC. It is not storing power in the long term. It merely allows us to transfer energy. What we will do is take the DC voltage, here termed UC1, UC2, and invert it through a voltage source converter to create a voltage source on the AC network. The voltage source converter itself uses self-commutating switching devices. These days we use insulated gate bipolar transistors, IGBTs. There are other devices available, but that is quite commonly used. These are fairly standard industrial switching devices. So again, they're not very special for DC applications. But it does give us the ability to turn a DC voltage into an AC voltage, i.e. that we're building an inverter. If we can control the AC voltage correctly, we can control both the amplitude and the phase angle of the voltage. So effectively, we become a de facto generator, albeit with no rotational inertia. But if we do this properly and control the phase angle of the voltage that we generate with respect to either network 1 or network 2, we can control the flow of real power between the two networks. If we can control the amplitude of the generated voltage on both network 1 and network 2 independently, we can control the flow of reactive power between the DC system and the AC system. So just like a synchronous machine, we can generate power, import or export as we will, and we can generate reactive power, both absorption and generation as we will. So we have all of the functionality of a synchronous machine, as I say, without inertia and without rotational mass. That is the simple principle of a voltage source converter. Two inverters separated by a transmission line, which can be overhead line or cable. And as Kevin has explained, we have both in this particular application. So if we look at the converter in a little bit more detail in the next slide. This is a very simplified topology of a voltage source converter. So we connect to an AC circuit breaker, 33 kV breaker in the existing substation. We do require an interface transformer. So this transformer connects to the 33 kV AC network. The secondary of the transformer is essentially a free choice of the vendor of the equipment. His task is to achieve plus or minus 27 kV on the DC bus, so he can choose the secondary voltage of the transformer as he will. As it turns out, because the DC voltage is essentially the peak of a 33 kV sine wave, this interface transformer is more or less a 1-to-1 ratio transformer. It would normally be a star delta transformer, just as would be normal. The heart of the technology is the power electronic valves. Here I've shown the symbol for an IGBT, and as I mentioned before, the DC capacitor is the transitory storage of energy. So having charged the DC capacitor up, we can invert that DC capacitor voltage through the power electronic valves to create a sinusoidal waveform at the secondary of the transformer. We have a converter reactor, or we may have a converter reactor. Not all designs need this. We will have a DC reactor. You've seen this in the layout that Kevin showed. There are DC reactors, one positive, one negative. So this represents the simplified topology of the MVDC circuit. And indeed, this is very similar to HVDC circuits, which are very much the same technology, but the details of equipment are quite different. For the power electronic valves, I've shown a single symbol for an IGBT, but of course there are many, many IGBTs in series to hold off the 27 kV DC voltage, not simply one switching device, but for the purposes of PowerPoint, I've just shown one. If you go to the next slide, I'll just run through some of these key features. The AC switchgear is standard medium voltage switchgear, nothing special. The interface transformer essentially gives us three functionalities. It optimizes the voltage in the power electronic converter. It does provide very important galvanic isolation between the AC and DC systems. So there is no path for DC current to flow from the DC side to the AC side, which is obviously good for the AC network. And it acts as an impedance to limit fault current into the power electronic converters. If there's a fault on the DC side of the converter, for whatever reason, fault current will be limited by the impedance of the transformer. So we don't destroy any equipment. We would trip under control and not cause any damage to equipment. The converter reactor, if we have one, would again control the current in the power electronic converter. Simply switching IGBTs on a DC voltage is not as simple as it sounds. So putting some inductance into the circuit can be quite important. But we could omit that inductor if the transformer can provide the necessary inductance. So not all designs need that converter reactor. The power electronic converter itself can have a variety of different topologies. Historically, two-level converters or three-level converters have been used, or multi-level converters are now becoming more common. And for the topology that General Electric are proposing for this project, they're looking at a multi-level arrangement to help produce a much better sine wave. The DC capacitor, which I've shown in my single line diagram, may not be a single DC capacitor. More likely, it will be segmented into small DC capacitors, each controlled by the multi-level converter. The DC reactor, again, is there to limit fault currents. If we have a fault on the AC side of the converter, the remote converter will pump in fault currents, or will try to pump in fault currents. And again, the DC reactor will limit the fault current that flows into the power electronics. And the DC bus, as we've now described, can connect either to an overhead line or a cable. And for this Angle DC project, of course, we have both. So if we move on to the next slide. This is one of the key functionalities of DC technology or VSC technology. On the x-axis, I've shown power. On the y-axis, I've shown power. On the x-axis, I've shown reactive power. Essentially, this technology can provide a constant NVA capability. We can import or export power as we will. We can import or export reactive power as we will. We do have a constraint. As we try to export capacitive reactive power, we have to increase the generated voltage, the magnitude of the generated voltage, and that puts voltage stress on the IGBT devices. So there is a limitation of voltage on the capacitive output. which limits our scope of generating capacitive reactive power. On the inductive side, we have to decrease the system, generated voltage, and decreasing the voltage never hurt anybody. So we have more scope on the inductive side to absorb reactive power. But the reality is that the MVDC link can operate anywhere inside the characteristic you see in this slide, the yellow-shaped area. So we can have full power and zero reactive power, or we could absorb full reactive power and have zero power transfer. So if for any reason we don't want to transfer power between the island and the mainland, we effectively have two STATCOMs at our disposal, one at either terminal. If the cable is faulted for some reason, has to be taken out for maintenance or repair, again, we have two STATCOMs, one at either side, which can be operated simply by isolating the switches, which Kevin showed in one of his slides. So the functionality of a voltage source converter is to give both real and reactive power control on the system. If we move on to the next slide. So just to give some of the applications and advantages of this DC technology, we have precise control of power. As Kevin mentioned, we will avoid loop power flows coming from the 400 kV from the nuclear station. So the megawatts that flow in a DC circuit are exactly as required by the operator or by automatic control. It cannot be increased or decreased inherently. It is a controlled flow of power. It also means the system cannot be overloaded. So we designed this for 30 megawatts power. That's what it will do. It will not take an overload unless you tell it to, unless it is capable of doing so. So it will not become inherently overloaded by some looped power flow. We can precisely control the reactive power. We can precisely control the reactive power, both absorption and generation. And this will allow Scottish Power to improve the voltage profile at both ends of the link. If we can improve the voltage profile, we can improve the losses in the local distribution system. I've mentioned we have an uplift of power compared with AC systems. We can also reverse power very, very quickly. I suspect we can reverse power too quickly for the AC systems to accommodate it, so we would have to slow that down. But power can be reversed in milliseconds through a DC link. It's the nature of the voltage source converter that to reverse power, we don't have to change polarity of the cables. We can keep the polarity as it was and merely change the current direction. So this can be done very quickly. I've mentioned the STATCOM mode. We can provide rapid voltage support to the AC network. So in the event of an AC network fault, we can automatically go into STATCOM mode. We can set the power to run to zero, so we don't feed the fault, and we could increase the STATCOM capability to maximum, or any other combination. The system studies will tell us what is the best control methodology here. Short circuit currents I've already mentioned. And again, Kevin has mentioned the integration into wide area monitoring systems. So we take multiple signals coming in from different parts of the grid and use that to optimize the performance of the MVDC link. If we move on to the next slide. Of course, there are some disadvantages which we should be aware of, and we'll evaluate these during the project. Operating power losses. We have losses in the converter technology. We've introduced a power electronic converter at both ends of the link. It was never there before. So the losses of the converters must be considered. And we've put in two new transformers that were not there before. So the interface transformer losses, i.e. the total scheme losses, must be considered. The benefit, of course, would be that the losses in the AC cable would be reduced because we don't have skin effects in DC, so we can make use of all of the cross-section area of the conductors. So the transmission losses would be lower, but the station losses would be higher. We must consider station reliability. Again, we've inserted power electronic converters into the system. We have a control and protection system. We have a cooling system. So in the operational phase of the project, we'll assess the reliability of this technology. Does it achieve high reliability, high availability of energy transfer, or is it wanting in some way? One issue that we are aware of is that the topology we're using is not well adapted to overhead line application. So if we have a fault on the short length of 27 kV, as it will become, DC overhead line, the topology itself, the power electronic itself, cannot clear the fault. So we'll have to open the AC circuit breakers, as we would do now with an AC system. Many HVDC stations can deal with such DC faults, but not the topology we're using here, and indeed not the topology that is widely used for HVDC applications. There are topologies that can clear DC faults. A full bridge topology, a more complex topology, could clear a DC line fault, but the operating losses and the capital costs will be higher. So we're going to see how this pans out. If we have suffered a lot of DC line faults, we may decide that this has not been a good application. If the DC line faults are within an acceptable bound, maybe this is a good application of DC technology. And we must be conscious of the environmental impact of putting an MVDC link into both Anglesey and the mainland. We need a building. Kevin's mentioned that height could be an issue for the building in a primarily agricultural or domestic landscape. We have to be conscious of audible noise. The transformers will bring additional noise sources. The cooler fans will bring additional noise sources to the two stations. These will have to meet local planning regulations. And Kevin has mentioned electromagnetic interference. The conversion process from AC to DC, from DC to AC, does create harmonic distortion superimposed on the DC side, for example. We need to quantify that to find out what harmonic currents will be flowing in the cables, primarily across the Britannia Bridge. But also we need to look at the electromagnetic environment in general. We need to be aware of radiated interference, AC side harmonics, DC side harmonics. So there's a big learning exercise from the implementation of medium voltage DC into a UK distribution grid. If we go to the next slide, which is the last slide. You may ask, why do it by DC? Some of the reasons we've obviously discussed in the last two presentations. Alternative solutions that could have been considered, or were indeed considered, I thought about at least. You could increase the power flow by adding in series capacitors. This is widely used on high voltage AC transmission lines. It's not a technology readily used in distribution systems, but it's a theoretical possibility. If we wanted to control that power flow, we could put a thyristor controller on the series capacitor. So a thyristor controlled series capacitor is a competing technology to a DC link. Essentially, you can control the power flow, increase the power flow using thyristor controllers. We could have installed a phase shifting transformer to control power flows. So this would change the phase angle between the island and the mainland grids, thus allowing us to more precisely control the power flow. Or we could have put in static synchronous compensators, STATCOMs, to control reactive power flow on the island grid and on the mainland grid. And essentially what we've done with MVDC is essentially it's a combination of a phase shifting transformer and two STATCOMs, if you like, would be the competing AC solution to an MVDC technology. So MVDC is a good solution for this particular application. It's a good demonstration of the use of DC technology in the UK distribution networks. But we are conscious that there are other AC solutions which could be available. I thank you for your time. That ends my presentation. I can hand over to Dr. Jun Liang of Cardiff University. Thank you.
Yes. So, Andrew, any?
Thanks for coming, Andrew. Bear with me 1 second.
That's okay.
Okay, June, carry on when you're ready.
Yes. So this last slide.
That one. This one here. Worked by Cardiff University. Yeah.
Okay. Yeah. Good morning, everyone. I'm Julian from Cardiff University. So Cardiff University is very happy to join this Angle DC project, just this kind of academic engagement. So the presentation is about the dissemination, because this is one of the main tasks we will undertake. Because through this industrial project, our project, the objective is to try to understand some of technology and make some academic contribution on some related topics, and also based on our existing expertise, and capture the knowledge and then disseminate the results through the publication, events, and also put some open source model which is available for future research or this development. Okay, thanks. Next slide, please. So this is actually the five tasks. So I'll briefly report some tasks in at Cardiff University. So next, please. Andrew, next, please.
Next one, task 1.1, June.
Yes, next, please. Yeah. So there were, in terms of this technical part, there were two tasks. The task one is based on this average model, optimal operation, and then to identify the benefits of the DC transmission in this AC distribution network. So in this, there are three subtasks. Subtask 1.1 is mainly to know this panel's demand and generation headroom. With this new technology, we will use our method to quantify this headroom. We have already developed some model and program based on the IPSA, which provides AI, that's IPSA, and also debugging some software for this development of this system. And in the future, also try to use Cardiff University's supercomputer to analyze the data and then quantify these benefits. So some of the paper we have prepared for CID, CERET, or some similar level to publish these results. We quantify the changes. Particularly, we are interested in this headroom, how much more we can connect loads and more to connect the distribution generation. Okay, next, please. Yeah, go to the next slide. Okay, the task 1.1 is mainly undertaken by Neil Thomas at Cardiff University, and then 1.2 is also for the real-time, the operation and control, and also identify the kind of headroom based on the control point of view. This task is undertaken by Chao. So several control ideas, for example, based on the information from the grid generator, from the wide area SCADA system, or from the local. So we designed the system to try to compare different control strategy, and also compare the different input information and the impact on this control performance in terms of the more power load connection, and then the DG integration, and try to identify using some mathematical methods to use the sensitivity method and identify the critical points, and also analyze the some more measurements, but only from this existing one. The more measurement points are needed through these kind of cost benefits methods. Okay, next slide. So the 1.3, the third task of this task 1, is also the multi-objective optimization. So use different methods to consider the power losses, consider the flow, and then also power control from the converters. This method has been already used for some of our research, for example, for the back-to-back, and then now we want to use it for the DC, embedded DC and AC system. And some methods, for example, particle swarm and taxi cab optimization method have been developed, and using the MATLAB link to Python, which try to obtain this optimization and identify the optimal operation points. So again, if the our objective is to increase the transfer capability of this network with DC-Link. Okay, next slide, please. So next slide, we will go into the task 2. There are 4 subtasks. So first one is the control of the voltage source converter. Norman has talked about some of the general knowledges of different level, high voltage level and then different type of converter. So before we know exactly some of the control configuration and the control strategy from the supplier, we have done something based on our expertise to build the model of the converter to design different controller used for this, to achieve the basic control objective and the normal operation and unbalanced, and also Statcom operation only provided reactive power and voltage support, and also consider the ripple, the performance at the AC side and the harmonics at the ripple at DC side, harmonics on the AC side. So we have already built some of the model, and then we can apply the model to this to the real angle DC system based on the supplies some parameters. Okay, we are go to the task 2.2. So this one mainly is about the selective converter control. How does this affect the AC system? For example, the AC fault current and some performance, and how does this affect this AC system? We need to build a model to analyze this fault current first, and then also analyze the how does this affect the protection and the automation. So Avinash has undertaken this work. Sorry, I forgot to mention the 1.3 is undertaken by Chichi, one of his students. This is undertaken by Avinash. Okay, next one is the 2.2. It's quite similar, but we have used a more detailed Parallel Charge model to test the fault, AC fault on this DC system, fault right through capability. So use the to also to investigate the effect on the protection and the restoration if the system is subject to a AC fault. So this is also task 2.2. So task 2.3 is on the next slide, please. Yeah, the protection and operation. So this protection, this work taken by Tibin, and the protection is on the DC. Say if the system is subject to the DC fault, as Karen Norman mentioned, because you can see the this cable and overhead line, and they could subject to not only permanent fault on the cable, but also some transient tightening on the overhead line. And also, if this technology, I mean this DC technology, will be used in the different location and other system in the UK, or even some this technology used to DC for example the overhead line. How do the converters deal with this transient fault, and then how do we identify and restore the system, and also consider this combination? This is quite interesting point of this particular project, the combination of the cable and the overhead line. So we have because we have already done some of the HVDC protection, so we will use some of the knowledges and apply to the medium level voltage, and then investigate this DC protection response, fault response, and operation. Okay, next slide, please. And so this one is about the reliability and then this operation of this DC-Link. As Norm mentioned, for the voltage source converter, there are different types: 2-level, 3-level, multi-level, and even multi-level, the different configuration sub-module. And all these different types of converters, they will have a different size, cost, and also reliability. How does this, how can this or one of them, the converter be used in this Angle DC project? We have done previously some reliability analysis on the voltage source converter, and then we can consider this angle DC specific case and then analyze the reliability. Because in the design stage, as Kevin said, we have already put some requirement on the reliability, and based on the historical data, we can use some also analytical methods to analyze the reliability, but also understanding some theoretical reason or principle behind its reliability, and then combine this analytical model and then this historical data, and then try to get a further and deeper understanding of reliability of this medium voltage DC. Okay, next slide, please. This is also reliability operation. So one of the issues could be, because the AC/DC, the medium voltage level is new. This is the first kind of this project in the UK, and then also there's some synchronous generator in that area, distributed generation, and future this nuclear power station. And is there any possible interaction? I mean, adverse interaction between this converter and these generators? Say torsional interaction, some other harmonic resonance, and if this really exists, and then what's the reason, and any possible solution? Because we have already made some similar issue for this converter connecting the renewable generation, for example, offshore wind turbine, some other wind turbine, some instability issue. So we want to investigate if this is also the possible risk in this area. So we try to make this analysis and contribution using some of our existing model. Okay, next please. Next slide. So because our task, the Cardiff is in this project is for the dissemination. So we will disseminate this through publication. We have already identified some of the target conference and then this journal, and to publish our results, working together with the different partners. This different IEEE, IET conference, and the journals, and also some other events. They joined organized events, and we can also through some different conference, we can organize the different events and then try to disseminate this result. Okay, and of course, finally, we can build some open source model based on this data, information, and knowledge, and some model which can be open for future seminar research and project. I think that's all. This one, okay. Yeah, final one.
Thank you, Jun. That's very informative, very interesting. Thank you very much.
Okay, yeah, thanks very much.
Okay, I'll pass you back over to Kevin Smith now to talk about further stakeholder engagement work we've been carrying out.
Okay, the good news is there's only one slide left, so before we go into questions and answers, and this is really just to touch on the stakeholder engagement. Dr. Jun has obviously told us quite a bit about the papers that are being produced, and obviously we're using the university as a centre hub for dissemination of academic papers to go out into the wider community. But on top of that, we've got the project website. If you can have some time to have a look at that, you'll find information on there about the project and presentations, and there's also a brochure that we've produced, which I'll mention in a second. We also do 6 monthly reports submitted to Ofgem as per all NIC projects, and they're published on the Ofgem website, so you'll be able to see information on them. To date, we've published 2 reports which are available given update positions. I'm also in contact regularly. I have a monthly update call with our project contacts, so they're fully aware of what's going on. We've got papers presented on the project at the AC/DC conference, where we had two sessions which focused on Angle DC and the outcomes. One was an overall view of the project, and one was more to do with the actual control analysis that we've done. We're also sharing this with internal staff. It's very important that we get the internal staff buy-in so that they understand the equipment, because at the end of the day, in the middle of the night, it will be the local staff who have to go out when something's not quite working or alarms come up, etc. So we're making sure that they're fully on board and see the project throughout its life cycle. Cardiff, I've just mentioned about some papers, and also SciRed 2017, which is being held in Glasgow. It's being hosted by Scottish Power, and we have a number of papers which are being presented there, and Angle DC is the main focus of those papers. We did iPad presentations for the LC&I conference. We produced bilingual brochures. These are available online if you wish to have a look at them. We did them bilingual because anything that we put out for the local community at Anglesey or in North Wales, we like to make sure that we make things in a bilingual arrangement for the people out there whose Welsh is their first language. And we've had a number of other meetings and touch base with other NIC projects. Most importantly, WPD's Network Equilibrium with their flexible power link is very much a mirror of what we're doing, but is a back-to-back. Slightly smaller, but very, very important learning, because they're slightly ahead of us, so we're in close contact with them. And the SSE HVDC Centre, which is just been opened up in Scotland, in Cumbernauld, is also a massive opportunity for us to work with them and share and collaborate on information. So there's quite a lot going on there in terms of stakeholder engagement. So hopefully this has been informative for you.
Okay, thank you, Kevin. That was very good. That brings on to our 10-minute Q&A session, which I'll chair, and I'll direct your questions to the most appropriate person. If you just want to try and get through one at a time, and I'll try and structure the queue for questions. So if you open up the floor, the first question, then let's go ahead. Okay, any other questions?
Quick one for you.
Yep.
It was mentioned earlier on that the DC system couldn't detect faults on the overhead line portion of the DC circuit. How are those faults detected and cleared?
Well, it's probably a split between Kevin, who's in discussion with the suppliers about how we're going to handle transient faults, and Norman with the converter capability and topology. So, Kevin,
I'll start first. When we say we can't detect faults, it's not like a normal protection system you would have on an AC. But what we can detect is leakage to earth. We're not expecting any pole-to-pole on this, given the fact that they're on two discrete circuits. They're not even intertwined conductors. So what you can detect is leakage to earth, and then the system then evaluates that leakage. I mean, we'll get some leakage to earth anyway, evaluates the level of leakage, and can automatically shut down the converter station. Fundamentally, we can remove the voltage off the output, and our plan is actually to try and retain some of the functionality that we would have with an AC overhead, particularly the overhead line system. Obviously, on a cable system, if you have a fault, you shut down and obviously go and test and see what's wrong. On an overhead line, at the moment, the current functionality is a 4-second auto reclose single shot. And what we're trying to do is see if we can actually recreate that situation through the software and the control mechanism for the converter. And the way we're envisaging this will work, it's under development, by the way, so I am really sharing my thoughts with you rather than any fact. And that is when, if there was a transient fault and it detects a leakage to earth and shuts down the voltage output of the converter station. And then when it comes back on, it actually does something which is called a pre-charge. And that means it actually ramps the voltage up on the overhead line and charges up the actors and the circuit and the conductors. And because there's quite a bit of capacitance in there. As it does that and it brings that up, if there is a fault that still exists on it, which invariably on HV systems, you get the voltage up to a certain point and then it'll kind of crack over or flash over. What we can then do is detect that there's been a sudden increase in leakage and actually shut the system back down. If that sudden rush of leakage doesn't occur, then we're going to continue with the pre-charge sequence up to full pre-charge voltage and then energize the line as you normally would. So we're hoping to try and retain a kind of auto re-energize feature. I'm loath to call it auto reclose because it's not quite the same, but this sort of auto re-energize following a transient fault. Because what we don't want to do is lose the performance of the circuit, particularly with a bit of overhead line in it, as over and above the performance that we would expect to get out of an AC current system.
Okay, Norman, do you have anything to add in terms of the converter technology capability?
No, just to perhaps re-emphasize the point I made earlier, that in an ideal world, if we had a fault in the DC line, we would simply block the converters, i.e. stop sending firing pulses to our IGBTs. So we would stop feeding current into the fault. But if you look at the model I included of an IGBT, there's a diode embedded in the design, and you can't stop a diode, unfortunately. So we can't block the fault current through the converter. So as Kevin said, the only way around this problem is to open the AC circuit breaker and go through a 4-second delay and an auto re-energization of the converter. So that should work quite well. We should be able to achieve, hopefully, as Kevin has described, the functionality of an AC auto re-energization system. Ideally, the DC could do this itself, but with the topology we've chosen for this first trial, it cannot. So we shall work out how to do it with the General Electric technology so that we can come back on fairly quickly in the event of a DC side fault.
Okay, thank you, Norman. That was very informative. Okay, so do we have any other questions?
It's Frank Clifton from Scottish and Southern Energy Networks. Just wondering how you've done the sort of last year's worth of work. Just wondering how the sort of costs and benefits you anticipated at the start. Are they on track, or are they? Because it looks like you've had a lot of technical issues, particularly with the railway crossing. So you're going to be able to sort of achieve the benefits you were looking at, or have you got any feel for that at the moment? Now you've gone and tested the market.
I think it's a bit early to say, to be honest. But what I will say is we're currently operating within budget. Obviously, we set out with a budget for the project. And the cost-benefit analysis that was done at the outset. On one hand, I would say you can make the figures stack up. On the other hand, if I'm trying to be realistic, the question is, what are you comparing it to? Because if we're comparing it to putting StatComs in, putting additional assets in, etc. So, you can lay it on thick or you can lay it on thin. But ultimately, I think what's more important in this is the trial of the technology and then evaluation of the rollout costs versus the trial costs and see what we can strip out and what we can take forward into a further duplication. In terms of the Network Rail aspect, it's an important one that, yes, we didn't fully appreciate the level of involvement that's going to cause us. And it is costing, some substantial chunks of money. And, we're into in excess of 100,000 just in consultancy costs for the various bodies that we talked about earlier on. We've also had to do acoustic surveys to look at the potential impacts of the noise of the transformer and converter station on local residents nearby. We didn't anticipate that. That hasn't been that great. But overall, there was some contingency in the project, as you can imagine, in these unknown waters. So we're currently fortunate enough to be within budget with the contingency available.
Thanks, Kevin. Just really quite interested in the sort of replication cost of sort of doing it without all the extra hoops you've had to jump through with the network relay, etc. So it wasn't a
Yeah.
criticism. It was a.
No, it's very fair comment, you know, and you know when we get to sort of the final year of the project and we're starting to tot up all the costs and then work out what costs are trial costs versus rollout costs, I think we'll have a clearer picture then of what the real overall cost benefit is.
Okay.
Also, the CSMRA process allows for the first instance of a study to be used as a reference case. So any subsequent similar problems, EMI problems, could use that reference case to bypass a lot of the consultancy costs and research costs.
Okay, thank you.
Okay, is there any other questions? We've got time for one more. No? Okay, thank you very much for taking part in the webinar, and we'll try and make it available online soon. And if you have any questions in the meantime, feel free to send me an email and we'll get them answered for you. But otherwise, thank you for attending. We really appreciate your input. And yeah, we'll be sending more updates online. So thank you very much for attending.
Okay, thanks.
Thank you.
Thanks, bye.